In the lexicon of naval warfare, the super dreadnought was the ultimate expression of national power. These were floating citadels, designed to trade broadsides with enemy fleets for hours, absorbing punishment through inches of case-hardened steel. The USS Arizona, at over 30,000 tons of displacement, was the embodiment of this philosophy. She was built to be unsinkable by anything less than a concentrated fleet action. But at exactly 08:06 a.m. on December 7, 1941, that assumption evaporated in a flash of violent physics. The Arizona did not sink after a prolonged duel. She was vaporized in a single heartbeat. Her destruction was not caused by a torpedo or a barrage of gunfire, but by one specific projectile, exploiting one specific geometric vulnerability that her designers had never adequately prioritized. It remains the most catastrophic structural failure in the history of the U.S. Navy. A fortress defeated not by superior tonnage, but by a conversion of kinetic energy that exposed a fatal obsolescence in battleship design. This is the story of the USS Arizona and the engineering flaw that sealed its fate. We will dissect how it was designed and why it failed. To understand why the Arizona died, we first have to analyze the geography that was supposed to protect her. In 1941, Pearl Harbor was considered a geographic fortress. The primary defense wasn't just the coastal artillery, it was the water itself. The harbor is exceedingly shallow, averaging a depth of only 45 feet. According to the naval orthodoxy of the time, this was a natural shield against aerial torpedoes, which typically required a drop depth of at least 75 feet to recover from their initial dive. Without that depth, a torpedo would simply bury itself in the mud. Furthermore, the Arizona was moored at F7, Battleship Row. Crucially, she was parked inboard of the repair ship USS Vestal. From a tactical perspective, the Vestal acted as a sacrificial shield. Any torpedo launched at the Arizona would strike the Vestal first. In the rigid calculus of pre-war planning, the Arizona was theoretically immune to the most lethal weapon in the naval arsenal. This forced the Imperial Japanese Navy, IJN, to solve a complex asymmetric equation. If they couldn't strike the Arizona's hull from the side with torpedoes, they had to strike her from above. But this presented a new problem: physics. Dive bombers, while accurate, carried lighter ordnance, typically 250 kilograms bombs, that lacked the mass to penetrate the thick armored decks of a super dreadnought. They would merely scratch the paint or destroy the superstructure, leaving the ship's vitals intact. To kill a battleship, you need to punch through inches of hardened steel to reach the magazines deep inside the hull. The only way to generate enough kinetic energy to penetrate that deck armor without a rocket motor is gravity. And to get that gravity assist, you need altitudes, specifically a drop height of over 3,000 meters. However, as altitude increases, accuracy degrades exponentially. Hitting a moving ship from 10,000 feet is statistically improbable, but the ships at Pearl Harbor were stationary. This variable changed the equation. The IJN planners realized that if they could perfect the optics of their bomb sights and the training of their crews, a high-altitude level bomber could theoretically drop a heavy, armor-piercing projectile straight down the smokestack of an American battleship. The Arizona was protected against a naval battle that would never happen. She was completely exposed to a vertical execution. To understand the inevitability of the disaster, we must virtually strip away the hull plating of the USS Arizona and look at the philosophy of her construction. The Arizona was a Pennsylvania-class super dreadnought laid down in 1914. Her design was governed by the standard type doctrine, which prioritized survivability in a line-of-battle engagement. The core of this defense was the all-or-nothing armor scheme. In this cross-section, we can see the logic clearly. The all-or-nothing principle dictates that the ship's most vital systems, the magazines, the engineering spaces, and the plotting rooms, are enclosed in a heavily armored box called the citadel. The belt armor here, along the waterline, is incredibly thick, up to 13.5 inches of face-hardened Krupp steel. It is designed to shatter a heavy shell fired from an enemy battleship 10 miles away on a flat trajectory. However, this design assumes the threat is horizontal. When we look at the horizontal protection, the decks, the armor is significantly thinner. In 1914, aerial bombing was science fiction, and naval guns lacked the elevation to drop shells vertically. Therefore, the Arizona's deck armor was designed primarily to stop shell splinters and debris, not a direct hit from a heavy projectile falling at terminal velocity. The total thickness of her protective decks was roughly 5 inches, but crucially, this wasn't a single solid plate. It was distributed across 3 separate layers: a splinter deck, a main protective deck, and a lower deck. While effective against fragments, this layered configuration is structurally weaker against a heavy, armor-piercing mass arriving from the zenith. This vertical weakness was the specific variable the Japanese engineers targeted. But they had a supply problem. The Imperial Japanese Navy did not possess a dedicated aerial bomb capable of penetrating a battleship's deck. Standard bombs had thin casings to maximize explosive filler. They would simply shatter on impact with armor plate. So, they improvised a weapon of terrifying ingenuity: the Type 99 No. 80 Mark V. This was not a bomb in the traditional sense. It was a recycled 410mm, 16.1-inch, armor-piercing artillery shell, originally manufactured for the Nagato-class battleships. To convert this artillery round into an aerial weapon, engineers performed a radical modification. They machined down the heavy body to reduce weight, installed a new aerodynamic tail assembly for stability during the drop, and crucially, retained the high-strength steel casing. The result was a projectile weighing 796 kilograms, 1,755 pounds. It had poor blast radius compared to a general-purpose bomb, but its sectional density was enormous. It was essentially a solid steel dart designed for one purpose: kinetic penetration. But the true lethality lay in the fuse mechanism. A standard contact fuse would detonate the explosive immediately upon hitting the deck, causing superficial damage. If the silver alloy hadn't fully penetrated the sleeve, a defect invisible to the naked eye, the joint would be a ticking time bomb. Compounding this vulnerability was the emergency surface system. To rise from the depths, a submarine uses high-pressure air to blast water out of its ballast tanks, regaining buoyancy. The Thresher relied on high-pressure air banks to do this. But the air piping system contained a subtle, overlooked choke point: the moisture dryers and strainers. These mesh filters were designed to keep the air clean, but they were about to prove catastrophically susceptible to the thermodynamics of expanding gas. As high-pressure air rushes through a narrow orifice, it rapidly cools, a phenomenon known as the Joule-Thomson effect. If that air contains moisture, it creates ice. So, as the Thresher sailed for her deep dive tests, she carried 2 dormant assassins: a piping network held together by unverified silver, and an emergency ballast system liable to freeze exactly when it was needed most. April 10th, 1963. The Atlantic Ocean, 220 miles east of Cape Cod. The surface conditions are calm, but 1,300 feet below, the Thresher is engaging in a deep dive test to verify her hull integrity. Hovering above her is the submarine rescue ship USS Skylark, listening via underwater telephone. At 9:12 a.m., the tests appear routine, but at 9:13 a.m., the Skylark receives a garbled transmission. Experiencing minor difficulty, have positive up angle, attempting to blow. To understand what happens next, we have to reconstruct the sequence of events using the forensic acoustics and our knowledge of the ship's systems. Somewhere in the engine room, one of those silver brazed joints, likely a small pipe, perhaps no larger than 2 inches in diameter, fails. At test depth, water doesn't trickle in. Driven by 600 pounds per square inch of pressure, the breach creates a violent, atomized mist. It screams into the compartment like a high-pressure washer. This isn't just a leak. It is a conductive saltwater fog that instantly coats the nearby electrical distribution boards. This triggers the first catastrophe. The main coolant pumps, responsible for circulating water through the nuclear reactor, trip offline due to the electrical short. The reactor's safety logic, designed to protect the core at all costs, senses the loss of flow and immediately triggers a scram. Control rods slam home. The nuclear reaction stops. The Thresher loses her primary propulsion. She is now a 4,000-ton steel weight, slowly sinking, drifting deeper past her test depth. Captain Harvey has one card left to play, the emergency ballast blow. He orders the high-pressure air banks to vent, pushing the water out of the ballast tanks to make the ship buoyant again. On the Skylark, listeners hear the sound of rushing air over the underwater telephone. The system is working, but then the sound stops. Here, the second catastrophe, the 1,500-pound mistake, occurs. As the high-pressure air rushes from the flasks at 3,000 psi into the ballast tanks, it undergoes rapid expansion. Following the laws of thermodynamics, the air temperature plummets instantly. The moisture in the air, which should have been removed by the dryers, hits the mesh strainers in the pipework. In seconds, that moisture turns into a plug of solid ice. The strainers clog. The airflow is choked off. The Thresher's attempt to surface is strangled by the physics of its own rescue system. Without propulsion to drive her to the surface, and without buoyancy to float her, the Thresher begins her final descent. She slides past 1,300 feet, then 1,500. The hull begins to groan. The steel is now compressing beyond its elastic limit. We can visualize the hull frames yielding, the circular shape of the submarine beginning to ovalize under the immense weight of the ocean.
At 9:17 a.m., a final distorted transmission reaches the Skylark. 900 N, interpreted by many as a depth reading exceeding 2,000 feet, or perhaps the start of the word Navy. It cuts off.
And ripping open
Milliseconds
the
later, the physics of the deep ocean claim their prize. The pressure hull collapses. This is not a slow crushing. It is an implosion. The water rams into the ship at supersonic speed, faster than the speed of nerve impulses in the human body. The air inside the hull is compressed instantly, creating a flash of heat rivaling the surface of the sun. The diesel fuel ignites. The entire vessel is shredded into thousands of pieces in less than 0.1 seconds. The men on board never felt the water. They were gone before their brains could process that the hull had breached. When the bathyscaphe Trieste eventually descended into the darkness to survey the grave of the Thresher, the crew did not find a submarine. They found a debris field spread over thousands of square yards, a confetti of shredded steel, twisted piping, and battery plates. This chaotic mosaic confirmed the violence of the end. The Thresher had not flooded slowly. She had been obliterated by the ocean's fist. The forensic analysis by the Naval Court of Inquiry was exhaustive, and the verdict was damning. The Thresher was not lost due to enemy action or a mystery of the deep. She was lost because of a philosophy that prioritized performance over quality assurance. The investigation identified the specific tragic flaw in the design, the reliance on silver-brazed joints in a high-stress, flexing hull without adequate verification. The 1,500-pound mistake was the failure to account for the catastrophic thermodynamics of the emergency blow system. The engineers had designed a system to save the ship, but had neglected to test it under the specific conditions of a deep-water casualty. The mesh strainers that iced over were too small, a minor component that cost the Navy its most advanced warship. But the Thresher's legacy is not her destruction.
It is the safety of every submarine that followed. In the wake of the disaster, the U.S. Navy created the SubSafe program. SubSafe halted the entire submarine construction pipeline. It established a ruthless doctrine of maximum reasonable assurance. Under SubSafe, a submarine's hull integrity is considered guilty until proven innocent. Every inch of pipe, every weld, and every valve impacting watertight integrity must have a documented pedigree, tracing the steel from the mine to the foundry to the shipyard. The result of this rigorous engineering penance is undeniable. Before 1963, the Navy lost 16 submarines in non-combat accidents. Since the implementation of SubSafe, the United States Navy has not lost a single SubSafe certified submarine to a material failure. The ocean is an environment of absolute hostility, a domain where the laws of physics do not negotiate. The Thresher taught us that in the deep sea, the margin between a technological marvel and a crushed tomb is measured in microns of silver and the temperature of expanding air. She remains on eternal patrol, a silent guardian whose sacrifice purchased the survival of every submariner who has dived since.